We are Team 18, and our topic is medical visual question answering. This is our agenda.
Here's the problem description. Visual question answering in healthcare faces challenges due to the inherently multimodal nature of healthcare data and its limited availability. Current approaches often treat Med-VQA as a classification task, which restrict adaptability to real-world scenarios. Our hypothesis is that reframing Med-VQA as a generative task can enable flexible models capable of generating clinically meaningful responses, advancing patient care. The VQA ROT dataset, curated by radiologists, include over 3,000 question-answer pairs covering diverse question types. With its balanced design and natural language questions, it serves as a strong foundation for training models to interpret radiology images effectively.
We now present the core ideas of our approach. We worked off the pre-trained M3AE model, which stands for Multimodal Masked Autoencoder. M3AE was trained with image-text input pairs. As shown here, both inputs were first passed through their own attention-based encoders, then the outputs of those encoders were passed through a fusion module, which uses cross-attention to force interactions between image and text representations. Then the outputs of this fusion module could be used for both masked image modeling and masked language modeling downstream. To evaluate M3AE on closed-ended Med-VQA tasks, where questions come with a defined set of possible answers, the authors added a softmax classification there at the end. However, treating medical question answering as a classification problem greatly limits the utility of medical QA models in the real world, as we discuss more later. The idea was thus to replace this classification layer with a generative head to improve the model's flexibility, especially on unseen data. Specifically, we used the T5 small encoder-decoder LLM. We tested 3 different input methods for T5. First, as shown on the left, we tried passing in both the M3A outputs as well as the tokenized original question into the T5 encoder. Next, we also tried passing in just the M3A outputs into the T5 encoder. We did this in 2 ways. M3AE outputs a single CLS token, which compresses both the image and text features, as well as its larger image and text feature outputs. So, as shown in the middle, we tried passing in just the CLS token to the T5 encoder, and on the right, we tried passing in all the M3AE outputs to the T5 encoder. Note that we unfroze both T5 decoder and encoder layers while fine-tuning so that it could learn to handle the differently structured inputs.
I'll discuss the evaluation metrics and results for our medical VQA model. First, we used BLUE and LUTIS score as key evaluation metrics. BLUE measures how closely the generated answers match reference answers by comparing overlapping n-grams, while LUTIS focuses on unigram overlap reflecting liquor. These metrics help us assess both the precision and liquor aspect of our model's answers. Next, we reproduced the baseline results using the M3A model, fine-tuned on the VQA dataset. Although slightly lower, we observed competitive performance compared with baseline model, and we also measured BLUE and LUTIS score. However, replacing the classification layer with T5 led to a drop in performance across all metrics. This is largely due to the small dataset size and the dataset being confined to the specialized medical domain, which poses challenges for T5's general vocabulary and encoder. Additionally, many answers in this dataset are single words, limiting T5's ability to generate complex answers effectively. Lastly, our experiments with various input combinations to the T5 encoder showed that multimodal inputs with both text and image features yield better LUTS and BLUE scores. And we are also still conducting experiments with this setting that uses both classification and text image features.
We still believe that treating Med-VQA as a generative task has real-world use case potential because of the limitations associated with treating it as a classification task, like a limited answer set, poor context understanding, and low adaptability. In terms of next steps, to actually improve performance specifically on the VQA RAD dataset, we would propose a simpler generative layer to capture the shorter answers, but to get overall better performance on generation in Med-VQA, we would need a larger dataset with longer answers for training.